This project focused on developing a system capable of solving a simple puzzle. The problem is as follows. Given a template RGB image, such as the one shown and its associated pieces, reconstruct the template when the pieces are initially presented in a bin, possibly in a cluttered and messy manner. The puzzle pieces are simulated as rectangular blocks, where the sub-image is pasted onto the four oblong faces of the block. The solution to this task requires the development of a full-stack robotic system. A number of important subtasks need to be solved. The robot must be able to effectively pick and grasp the puzzle pieces, identify the image on the block, and place the puzzle piece so that the desired image is accurately reconstructed. These tasks are executed in a sequential manner and repeated for each block in the puzzle. In solving these tasks, a number of repeated subproblems must first be solved, such as object pose estimation and motion planning. The system also employs the use of a range of low-level behaviors and motion primitives, which are used and reused to operate the arm and manipulate the puzzle pieces appropriately. As you can see, there are quite a few cameras in the scene. The cameras are grouped and correspond to 3 stations. In the picking station, we use the point cloud depth readings to identify appropriate grasps. Because there is no guarantee on the image content of the blocks, we don't use the RGB channels here. An objective function is formulated, which positively weights alignment of the gripper normals with the point cloud normals, and negatively weights the distance of the contact point to the center of the block face. Knowledge of the block shape and dimensions are used, along with a simple method that uses graph partitions and convex hulls to determine the centers and alignments of the block faces. This promotes grasps that are antipodal and torque balanced at the contact point. In the next station, we identify the block and associate it with the template block in the desired image. First, a multi-step algorithm is used to align the block with the cameras, which enables a head-on, non-sheared snapshot of the block surface. The algorithm first uses a sequential form of ransack to identify planar surfaces in the point cloud. Next, the associated rectangles and areas are calculated via a convex hull method. The rectangles are used to construct a fairly accurate estimate of the block pose. This estimate is used to initialize ICP, which then fine-tunes the pose estimate. After alignment, an RGB image is taken, which is then filtered, segmented, and rescaled. To perform template matching, the image is discretized into a number of cells. For each cell, a histogram of the RGB values is determined. These histogram vectors are then compared with the histogram vectors associated with each template block. The template block that minimizes the histogram error is identified as the appropriate corresponding block. This association is then used to decide if the block should move on to the third station, which is a storage area. This decision will depend on the placing strategy used by the robot. In this implementation, the robot attempts to solve the puzzle from left to right and from bottom to top. As such, if the picked block is not the next appropriate piece in the strategy, it is stored in the holding area. The ransack ICP algorithm is used again to log the pose of the stored block. Once the stored block is ready to be placed, the robot recalls the stored pose in order to accurately repick the block. Once the proper block is picked, it is rotated if necessary and then placed in the desired placement position. The required rotation of the block is determined during the block identification stage. A series of simple but effective pushing primitives are then used to coax the block into the proper position. Here, the walls of the construction area are used to enable generally robust pushing. The end effector need only push the pieces in the right direction and can tolerate over-pushing. This simple procedure allows for a tightly aligned and adjacent placement protocol that would be difficult to achieve with other strategies. This process is repeated for each puzzle piece and cycles until the image is reconstructed. The end-to-end system will often alternate modalities between picking, identifying, storing, repicking, placing, and pushing. An interesting difficulty is presented when the block to be placed is upright. In this case, a simple primitive is used, where the block is rotated so that when released, it falls into the correct orientation. The modular sequencing of primitives and template-agnostic procedures enables the robot to solve generic puzzles of this form for any given image and number of puzzle pieces, so long as the number of pieces can fit into the workspace. Next steps for this work include expanding the procedure to work with heterogeneous and oddly shaped puzzle pieces, as well as exploring more complex, potentially learned block placing strategies. Replacing the geometric object detection algorithms with deep learning-based approaches would also likely improve the performance, robustness, and generality of the system, by enabling the robot to appropriately manipulate a less constrained class of objects. Videos of the puzzle robot in action are now shown for 2 additional puzzles. As these videos play, I would like to quickly thank Professor Tedrick, Terry, and Meng for a fantastic semester of 6881.